Hi, my name is Ben Corrado. I'm with Wirepas. I'm going to tell you a little bit today about some of the interference tolerance prevention techniques that we've implemented in Wirepas, why they'd be beneficial, and some of the solutions you're doing, and then a bit about a few real world examples that we have to kind of show you how that works. So, in Wirepas, we've really focused on building a decentralized mesh network. That means when the device is powered on, it scans the network and receives data from the other routing devices around it, which are in range. And that device then chooses the routers that it connects to that have the best path to the gateway. That device can also become a router of that network automatically and becomes an access point for everything else to be able to route through if necessary. And as the device is moved, it automatically finds new routes to that network. And even if other devices in the network are removed, it will find an alternate path through that network. By default, everything that comes from Wirepas is set up to be a router. So one of the pieces that becomes really important when you're building out these mesh network systems is making sure that they're very dynamic to the environment. So other interferers, other 2.4 gigahertz devices out there, Wi-Fi, Bluetooth, Zigbee, cordless phones, baby monitors, any of that type of stuff. We need to make sure that we're able to route our data around it and provide high level of reliability. We also have to be friendly in that we don't damage the spectrum for those other devices. So we don't want to be a harmful interference. So that means we have to kind of take all of that into mind as we're building out these networks. So when we take a look at the 2.4 gigahertz spectrum, it's broken up into different channels, kind of depending on what technology you're using. So Wirepas, we use 40 different channels spread out on a 2 megahertz spacing, and they're 1 megahertz bandwidth per channel. So 1 megabit per second is what we're using. Zigbee and Thread use 802.15.4, which has 16 different channels spread out throughout the 2.4 gigahertz space. Bluetooth Mesh uses 3 channels, the advertising channels of Bluetooth. And then Wi-Fi has 11 to 14 channels, depending on what region you're in the world, and also spread out with essentially 3 non-overlapping channels in most parts of the world, being 1, 6, and 11. So when we look at these pieces, what we need to figure out is how do you take advantage of the spectrum that's out there, and how do you make sure that you aren't interfering with these other devices out there so that they can't work as well. So that becomes a problem when you get into these corporate environments and enterprise and industrial solutions. There's often a lot of noise out there already. So Wi-Fi is one of the main contributors to these noise pollution, if you will, in the 2.4 gigahertz space. You get lots and lots of access points out there, and all of a sudden the noise floor of the system is quite high. And when you're operating with low power battery operated devices like we do in the IoT space, that means that you need to do retransmissions, you need to transmit at higher powers, and sometimes you can't even get through because the noise is so high. And so you need a system and a network that is very resilient to that. So in the enterprise space and the industrial and corporate worlds, Wi-Fi is typically deployed in kind of a cellular pattern, if you will. So effectively, you alternate channels 1, 11, and 6 to build out these cellular looking patterns. What that means is that kind of everywhere in the building that you're putting these IoT networks in, you're almost bound to get some interference because you're covering almost that entire spectrum. So if we jump back here and look, we'll see that there's a brief space in between channels kind of 3 and 4 as it's labeled here in the Wi-Fi, and 8 and 9. It's actually a little narrower than that if we jump back. And if you look at kind of where things are positioned, Bluetooth has chosen that on either side of channel 1 and on the outside of channel 11 to place their advertising channels for their Bluetooth mesh. And so what this means is that you're least likely to get interference across an entire building or campus because you're staying away from the common channels used of 1, 6, and 11. You can kind of see here that there's that 6 ramps down the band edges of 6 and 1 is where that middle channel is slotted. So that basically the effect there is you're shooting to be able to cover the entire building with 1 to 3 of those channels. You effectively repeat all the messages on all 3 channels. And you're limiting the amount of bandwidth that you can have with that. So when we look at kind of where Wirepas and Bluetooth stack up on the mesh front, Bluetooth using those 3 channels, full power, repeating all the messages on all channels, and basically doing a forward fire and forget, and then a pushing out repetition through a flooded mesh topology to hopefully get that message out to the network. Wirepas, we take a very different approach to this. We want to use all 40 of those channels and make sure that we are actively looking at what is not having interference on it and moving nodes in the regions where that interference exists away from it and onto free channels. So effectively what this means is we get almost 40 times the amount of throughput capacity network wide that a Bluetooth mesh can, because we can take full advantage of all of the channels. Zigbee operates on a kind of similar topology in that it's a single channel, but it's one channel without any of that repetition, and there's really no active avoidance of Wi-Fi across the campus like Bluetooth has tried to do. And so effectively, when you set up your first node on your Zigbee network, it goes out and it scans. It says what's the freest channel in the place that this node is scanning, and then it builds the network on top of that channel. You can change that channel later, but it means every node on the entire network has to change, and you only have 16 channels to do that. So effectively, somewhere in your campus, you will have interference as you're rolling out these 802.15.4 networks. If you're deploying them, and that's true on both Zigbee and Thread. They both use the same underlying protocol, and so again with Wirepas, you're able to really choose the network is self-choosing individual channels and dynamically routing between what we call clusters to pass those messages between routers, even if they are talking to their nodes on different channels. So this gives you a lot more capability and a lot more resistance, and effectively means that you can avoid all of these Wi-Fi signals out in your networks. So practically, what does that look like? We've got a couple different examples we're going to go through today. One is a chain topology, which I'm showing here. This is based at one of the employees in Finland. This is him and his neighbors have set up this giant long chain network to be able to do regression testing on how our network performs in these massive chains of 40 to 50 plus nodes. So as you can tell, there's lots of single point failure opportunities in this network if it doesn't self-heal, if it doesn't automatically reroute, that type of stuff. So this is one of the places we use to test. You can see we have a couple red dots in here, which are representing some of our nodes with low batteries, and basically that alternate between forcing things to automatically self-heal. So from a topology perspective, this is what that network looks like and how that actually routes data from an end device all the way up to the sink, which is the far left node. So from a RF perspective, what does this actually look like? So I took and used our Wirepas network terminal to get a week-long view of what was going on in all of these devices out in the field. And on the x-axis here, we have time over the week, and on the y-axis, we have the whole 2.4 gigahertz spectrum that's available in ISM bands. And you can see that the nodes are actively operating on many different channels. So we are using all but 4 channels of those 40. So 36 channels in this network during this week were in use at some point in time. You can see that they also hop around based on interference. So a node will have some interference from something and automatically change channels with its neighbors in order to resist that and to help spread out the network traffic across the frequency band. So there's 145 nodes in this particular network. And hopefully that gives you a little bit of a feel for, even on these kind of long chain topologies where there isn't probably a lot of interference, like in an outdoor environment like we're seeing here, that we're still taking advantage of all of these different network channels to give network capacity as well as interference resistance. So the next one we'll look at is an in-building. So this is one of our facilities in France. The nodes here are on multiple floors. There's multiple companies in this building. So there's lots and lots of Wi-Fi interference and other 2.4 gigahertz noise that happens on a regular basis in the building. The topology looks like this. I believe there's between 30 and 40 nodes in this particular network. And you can see that this one also has quite a large usage of the channels, even though it's a much smaller number of nodes. And there is quite a bit of hopping depending on when you are in the week, showing kind of the how the network spreads itself out, both from a load perspective and hopping to avoid interferers. So, I hope this was helpful to kind of help you understand a bit about what we're doing at Wirepas and how we're taking advantage of all 40 channels in the 2.4 gigahertz space to actively avoid interference and to make sure that other devices aren't interfered by Wirepas. And that's really our goal, is to make a very resilient, friendly network that's able to transmit your IoT data through the network reliably. If you have any questions about these particular examples, let me know. We can make this network, both of these networks are in our demo pool. So if you'd like access to get in there, look at all that data yourself, and understand a bit more about how Wirepas works in that regard, we'd be happy to set you up with that access. Shoot me an email at ben.corrado@wirepas.com or sales@wirepas.com will get us as well. And we'd be happy to get you set up with some information about how Wirepas works and the different ways that we've built in these resiliency pieces that make it really friendly to deploy in your enterprise and industrial environments. So thanks for watching. I hope you learned a lot. We'll be putting out more of these videos shortly. Thanks.